Hi everyone, thank you for joining our talk. We are happy today to share our notes on the exploitation of zero-day WebKit vulnerabilities on the PlayStation 4. Here is the outline of the talk. After a brief introduction, we'll present the PS4 attack surface as well as the previous research in this field. Then we'll present our bug. And the exploitation of that particular bug requires a deep understanding of the primary heap allocator, so we'll present how fastmalloc works. Then we'll present our exploitation strategy and give a little demo. And finally, we'll conclude this talk and present what we planned next. Before we start, let us introduce ourselves. I'm Mehdi Talbi, and I will give this talk with Contamefre. We are both security researchers at Synactive, an offensive security company based in France, and we are both part of the reverse engineering team working mainly on vulnerability research. Okay, this is important. Please note that we do not that this research is done purely for educational purpose, and we do not help, support, or endorse by any means to break the copyright law. Okay. Now, how all of this started, our internal fuzzer have reported a WebKit bug, and we decided to give it a try on a device like the PS4. Why that? Because despite an active console hacking community, there is only few public exploits, and we wanted to know how hard is it to exploit such a vulnerability on a device like the PS4. So the main goal of the talk today is to give a walkthrough on the exploitation of a zero-day WebKit vulnerability on the PlayStation 4. Okay, now let's move to the attack surface part. Here, the browser is probably the most common entry point. That's what we did. We can also attack the PS4 through game saves, or decide to attack directly the kernel, which is actually a FreeBSD kernel. For example, one can attack the USB, Wi-Fi, or the Bluetooth stack. Now, if we consider attacking a userland process, a typical exploit chain combines a WebKit exploit to get code execution in the context of the render process, then find a way to bypass the sandbox and run a kernel exploit. Now, as we say, the PS4 browser is based on WebKit, and the renderer process is sandboxed. There is no JIT, which means that it could be a little bit harder to get code execution. However, there is no modern mitigation like GigaCage or the randomization of structure ID, which means that it could be easier to set up a primitive like the fake obj primitive. ASLR is enabled. However, it is either weak or partial. This is at least true on version 6. And the most annoying point, there is no debug. Okay, now there have been a couple of WebKit vulnerabilities that have been successfully exploited in the past. The first one presented here is the last known public exploit. It is also known as the Bathhoist exploit. It exploits a vulnerability found by Lockyhart from Project Zero, and the exploit and this vulnerability has been exploited by Fire30. The exploit provides read-write primitives and works on firmware up to 672. Another vulnerability found by Lockyhart have been exploited by Spec2Dev. This one provides also read-write primitives and works on firmware up to 620. And for all the firmware, there is a couple of exploit found by a couple of exploit by QWERTY, Spec2Dev, and Citrus. Okay, now regarding kernel exploit, the last released one has been reported by The Flow. The exploit provides read-write primitives in the kernel. One interesting point is that it is reachable from the WebKit sandbox. And this bug is present in firmware 702 and also on firmware 6. And recently, this bug has been combined with the Bathhoist exploit to get a full chain on firmware 6. And finally, there is some few vulnerabilities in BPF that have been discovered and exploited by QWERTY. They work on firmware, this exploit work on firmware up to 5.07, and we strongly encourage the audience to read the excellent rated by SpectreDev. Okay, now let's talk about the bug. The bug is present in the WebKit DOM engine. It has been triggered by our internal fuzzer, and this bug impacts all PS4 firmware and PS Vita as well. We have reported this bug to Sony through their bug bounty program, and now this vulnerability is fixed on version 8. This vulnerability is present in the build bubble tree method called on some validation message instance. And this function makes at some point a call to update the layout, during which all user registered JS handlers are executed. Now, if we destroy the validation message instance during a JS callback, this could lead to use after free situation when getting back to build bubble tree code. Actually, the WebKit developer have identified that problem may arise while updating the style or the layout. However, they failed to fix this bug properly due to an extra reference while making a weak pointer, which means that we can still destroy the validation message instance during a layout update. And here is the actual fix after reporting the validity, after reporting the bug. Now they do not allow anymore to update the layout in build bubble tree code. Okay, now let's see the vulnerable path. We can instantiate a validation message object by making a call to report validity on some HTML input field. We register on that input field some JS handler. For example, we can define a JS handler that is executed whenever the focus is set on that input field. And then this function report validity will also fire up a timer to call our vulnerable function, the build bubble tree. And if we set the focus on our input field before timer expiration, then build bubble tree will make a call to update the layout, and update layout will call our JS callback. Now, if we destroy in this JS callback the validation message instance, then this could lead to use after free situation when getting back to build bubble tree. Now, if we manage somehow to survive to early crashes due to access to invalid validation message fields, we can end up by calling this function delete bubble tree after some timer expiration, and this function delete bubble tree will destroy again the validation message instance. Okay, now let's see how we can trigger this bug. The first step is to register a JS event on some input text field. Then the second step is to call report validity on report validity on our input text field. Report validity will instantiate our target object, the validation message object, and then we, in our JS handler, we will simply define, we will simply destroy the validation message instance. And then when build bubble tree will be called, it will make a call to update the layout, and which in turn will call our JS callback. We ran that code, but it didn't crash. Actually, the report validity methods sets the focus on our input field, which triggers our JS callback too early. So in our second attempt, we decided to use two input fields, input 1 and input 2. On the first input, we register a JS handler, handler 1, that will simply set the focus elsewhere. Then we make a call to report validity that will instantiate our target object. Report validity will set the focus on input 1. Our handler 1 is executed. It will set the focus elsewhere, for example, on input 2. And then before timer expiration, that is before build bubble tree code is executed, we register a new handler that on input 1 that will destroy the validation message instance. Then when build bubble tree code, when build bubble tree method is called, it will make a call to update the layout and run our JS callback and destroy our validation message instance. And we run that code, and it actually crashes the PS4 browser. And here is what looks like the PS4 when the browser crashes. Okay, now all we get are crashes and we do not have debugging capabilities on the PlayStation 4. So to overcome these limitations, we have two options. Option one is to set up a debugging environment as close as possible to the PS4 environment. That is, installing a free-based debug and compile WebKit from sources downloaded from PlayStation website. This is helpful, but sometimes a working exploit on our environment does not mean that it will work on the PS4. So clearly here we need more debug. So we decided to use option 2 and debug our 0-day using a 1-day. And for that purpose, we use the bad host exploit by Fire30 because it provides useful primitives like the read-write primitives, but also the classical added off and fake off primitives. However, the bad host exploits works only on firmware 6, and sometimes running the bad host exploit prior to our exploit adds some noise on heap shaping. And finally, the bad host exploit is not reliable, but all of this is fine. Okay, now let's see the vulnerable object, the validation message object. This object is instantiated by making a call to report validity. It is mainly accessed by the vulnerable function build bubble tree, and it is finally destroyed by the delete bubble tree. The validation message object is fast mallocked and is made of the following fields. The yellow one are instantiated or gets reinstantiated after a layout update. And the rest of the fields, the green one, are accessed after a layout update, and they point to some HTML element instance. Now, what is the situation after destroying the validation message instance in our JS callback? We have, when getting back to build bubble tree code, after calling our JS handler, we have to use after free. This and M element are freed. Most of the fields are set to null pointer, and M element is deleted, but we still get a reference on it. The situation is that we crash on the first virtual call on mbubble when getting back to build bubble tree code. And this situation is not really good. So to exploit this vulnerability, we need either a memory leak or find a way to bypass ASLR. And it turns out that we can bypass ASLR by just heap spraying some object. If we spray a couple of objects, they end up allocated at some predictable location. And here in our tests, spraying 2 MB is enough to predict some heap address. However, this requires a prior knowledge on the memory mapping, and this work, that's what we have on firmware 6, thanks to the bad host exploit. And this may work on version 7. We will discuss this later. Okay, now how we can survive to an early crash. The first step is to spray a couple of HTML elements. And by doing that, they end up allocated at some predictable location. Then we shape the heap so that we can reuse our target object and fix the mbubble and M element value so that they point to the address that we predicted. So this way we can survive to the early crash. Now, if we survive to that crash, we end up by calling this function delete bubble tree after some timer expiration, and this function will set to null pointer most of the fields of the validation message fields. And the null pointer assignment on brief counted classes is overloaded and results in a ref count decrement. This means that if we manage to reuse our target object properly, we end up we have a ref count decrement on multiple controlled validation message fields, which means that we can turn our initial use after free into an arbitrary decrement, and this is exploitable. Now, the exploit requires multiple heap shaping and spraying stages, and in order to be able to reuse our target object, we need to know how fast malloc works.
Now that we know which primitive the bug gave us, we must find a way to reuse the validation message object. This part talks about the fastmalloc allocator, that is the one used to allocate a validation message object. WebKit has many allocators. Fastmalloc is the standard allocator. It is used by many WebKit components. EasyWeb is used by the DOM engine. Its purpose is to sort each allocation using their types to mitigate user-free vulnerability. The garbage collector is used by the JavaScript engine to allocate JavaScript object. ISO subspace is also used by the JavaScript engine. It is very similar to ISOHEAP, but it is used for a few objects. And the gigacage is used to prevent out-of-bound read and write on specific object. For example, the backing buffer of the array buffer used this allocator, but when the gigacage is disabled, the allocated object uses fastmalloc. And the gigacage is disabled on every PS4 system. WebKit has 4 important structures. The top one is the heap. It is made of chunks. Chunks is split into pages. A page has a size of 4 kilobytes and it is divided into lines. And the line is the most important object for us because it is the one that holds objects. An important point is that lines are sorted into a page using the object size. So this means that we cannot have 2 objects that have a different size into the same line. And this means that if we want to reuse our validation message object, we must use an object that has that has the same size than validation message. Fastmalloc is a very basic bump allocator. It has a fast pass and a slow pass. The fast pass just uses a bump to store each object, and when an allocation request is made, it just pops an object from the bump. But when the bump is empty, then fastmalloc uses the slow pass. The slow pass is a bit more complex than the fast pass. Its goal is to refill the allocator. To do so, it will use several methods. For example, the slow pass will look in many cache if there are objects available to refill the allocator. And if these caches are empty, then fastmalloc will look in specific pages if some lines are released. And if they are, fastmalloc will use this line to refill the allocator. At the end of this pass, fastmalloc has a full bump allocator. A full bump. When an object is released, it is pushed in a dedicated vector that is named m_object_log. This vector is not made immediately available because it is processed only when it reaches its maximal capacity. Chunks, pages, and lines are ref counted. This means that they are released only when the ref count is equal to 0. So a very important point is that if we want to reuse our validation message object, it must be on a line where each objects are released. Otherwise, the line won't be reused. We can now start the exploitation part. As using the previous information, we know that we must control the full line where validation message is allocated in order to reuse it. To do so, we will allocate object that has the same size than validation message around it. before we will allocate them before and after allocating a validation message. We will end up with the following memory layout. Then we can release the object that allocated before and after validation message and the validation message itself. This will release the associated line and cache the page. At the end, we can now spray the final object that will reuse validation message. We choose to use the backing buffer of the array buffer. Why this object? Because first it allows to do an allocation using an arbitrary size, and we can read and write every byte of this object. At the end, we have two references that point to the same memory area. The first one is the validation message one, and the second one is the array buffer contents. As Mehdi said previously, three fields of validation message are allocated after reusing the object. So using our array buffer, we can read their value and get an initial memory leak. Two of these fields are allocated are pointer allocated using either heap, but they are not important for us. But the third one, the timer one, is a pointer allocated using fastmalloc. And this one is interesting, and we will reuse it later to guess the address of fastmalloc objects. We can now trigger the arbitrary decrement primitive. We can do it usually using our array buffer reference by just writing into the backing buffer. For example, we can corrupt the pointer of m_message heading, and when this pointer will be released, the ref count at this pointer will be decrement. Our strategy to exploit this primitive is to decrement a length in memory in order to enlarge a data buffer and get a better primitive like a relative read and write. To summarize our exploit strategy, we will trigger one first time the vulnerability and use the arbitrary decrement to get a first relative read primitive. We will use this primitive to find the address of a better objects in memory. Then we can use one more time our vulnerability and the arbitrary decrement to get a better primitive. This primitive is a relative read and write. And with a relative read and write, we can achieve arbitrary read and write and get code execution. The goal of the relative read primitive is to leak the address of JS array buffer view. JS array buffer view is an interesting object because first it has a length field and it allows to read and write arbitrary data. So if we can overwrite the length field, then we can read and write arbitrary data beyond the limit of the data buffer. To get the relative read primitive, we will use another object that is named string impl. String impl is the string representation, is the representation of a string in JavaScript. In JavaScript, strings are immutable. This means that we can read in the data buffer, but we cannot write data. And also, string impl is interesting because it has a length field and it is fastmalloc, so we can usually find it using our timer leak. So to override the length, we will spray string impl that has the same size than our timer leak. We will spread them around the timer object. Using our arbitrary decrement, we will overwrite the length field, and thanks to that, we can read beyond the limit of the string buffer. How to leak a JS array buffer view pointer. It is important to know that DOM objects and JS objects use two different allocators. So we cannot access to the JS objects using our relative read in fastmalloc. But JavaScript built-in that is named object.define_properties allow to allocate two objects, a vector and a marked argument buffer. Both objects are allocated on fastmalloc, and they allow to push JavaScript object reference on the fastmalloc heap. So using our relative read, we can usually find this pointer. To do that, we will allocate multiple JS array buffer view. Then we will push the reference on fastmalloc heap using object.define_properties. And then we can scan the heap using our relative read and find this pointer. To summarize, we have an arbitrary decrement and we have a JS array buffer view leak. We can now get a relative read and write primitive. We will just run the exploit again, use the arbitrary decrement on the leaked JS array buffer view RS, enlarge the length field of the JS array buffer view, and this allows us to read and write beyond the limit of the data buffer. So now, using a relative read and write, we can achieve arbitrary read and write. We will use another JS array buffer view. JS array buffer view has a vector field that represents the data buffer where we can read and write. So using our relative read and write, we will just overwrite the pointer of the vector, and using this we can read and write at arbitrary address. On PS4, we cannot allocate RWX memory pages, but we can control the instruction pointer. For example, we can just leak an HTML element object, overwrite its table pointer, and call the associated JS method that will trigger the overwritten pointer. And then we can implement the next stages using code reuse. Most of the previous PS4 jailbreak used this method. So this is time for a demo. So the exploit took about 11 seconds to reach arbitrary read and write. And at this moment, we reach arbitrary read and write, and we can start to implement the next stages. So to conclude, the exploit works on version 6 of PS4 firmwares. The exploit code is available on the Synective GitHub. The exploit is not really stable, and it took about 11 seconds to reach arbitrary read and write, but the reliability could be improved by, for example, improving the ASLR brute force step. And we can also find a better exploitation path that avoid triggering 2 times the vulnerability. We tried porting this exploit on version 7 of the PS4 firmwares, but we did not succeed. The ASR bypass did not work on this firmware version, and we only get crashes. But we tried to brute force the ASR using a Raspberry Pi. The goal was to guess the address of a sprayed HTML element, and the Raspberry Pi was used to emulate a keyboard and reload the page every 5 seconds after a crash, but we did not get any results so far. Thanks to Synactive for letting us do the research. Thanks to our colleague for all the help while developing the exploit. Thanks to Black Hat for the great event. And thank you for your attention. Do you have any question?